Hi class, in this video here we're going to move into section 3.3 and it's talking about the missing member. And there's this mathematician named George Cantor and he answers, are some infinities larger than others? And that's like not, doesn't really make much sense initially, right? Because, if something goes on forever and we're talking about something else that goes on forever, how could one be bigger than the other? Okay. So, is there an infinite set, quote unquote, bigger than the natural numbers, right? So, we've learned in previous sections natural numbers one, all the way two, three, four, so on and so on. So, is there a set, bigger than that? Well, the natural numbers are already an infinite number. So, how could there be a bigger one? All right. So, around 1872, this German mathematician Cantor shook the foundations of infinity when he showed that the set of natural numbers has more elements than the set of natural numbers. Proved that the set of real numbers, has more elements than the set of natural numbers. So, in other words, he proved that infinity is not one size, but that some infinities are more, quote unquote, infinite than others. All right. So, to show that the real numbers are more numerous than the natural numbers, this Cantor, he focused intently on what it would mean for the real numbers and the natural numbers to have the same cardinality. So, it would mean that the real numbers and natural numbers could be put into a one-to-one correspondence. Okay. Like have we been talking about in the previous section. So writing down what such a correspondence might look like gives us a visual clue as to why any attempted correspondence between the natural numbers and the real numbers could not include every real numbers. Okay, some real number is missing. So basically what I'm going to show you is I can prove that, however you want to write the correspondence, I can find a number that a real number that's not there. That means there's a number that exists that doesn't map to the natural numbers. Okay. Like we showed in the previous lecture, right? If you look at the natural numbers and then the even natural numbers, you might like intuitively think, well, the natural numbers 1, 2, 3, 4, all the way to infinity must be bigger than 2, 4, 6, 8, 10, 12. But we could do a one-to-one correspondence so they had the same cardinality. Well, there's a trick here we can't do with the real numbers, and you'll see. All right, so just so we're clear, what exactly is a real number? So real numbers are all the rational and irrational numbers. So if you look here, this outer oval here represents all the real numbers. So real numbers include the natural numbers, 1, 2, 3, 4, da, da, da. It includes what are classified as the whole numbers, which are the natural numbers and zeros. The integers, so the whole numbers and then negatives. Rational numbers, right? Numbers that can be written as fractions. And then irrational numbers, right? These are numbers that cannot be written as fractions, just decimals, non-repeating decimals that go on forever. So the real numbers include all these things. All right. And you can see here, right? Like, if you just think about, how big the circles are in here, like intuitively, it's just like, oh, obviously the real numbers are bigger. Okay. All right. So here's the easy way to explain it. Okay. So infinity can have different sizes. So most people think of infinity as just one big endless number, but Cantor showed there are different sizes of infinity. For example, the set of all natural numbers is infinite, but there's another infinity that's larger. And I'm going to show you it's the set of real numbers, which include all the decimals, okay, and non-repeating decimals. So the easiest way to think about this is what are called countable versus uncountable infinity, okay? When something's what's called countable infinity or infinitely countable, this is when you can list all the elements one by one, like the natural numbers. Even though there are infinitely many, you can quote unquote count them, even if you would count them forever. Like I go 1, 2, 3, 4, 5, 6. Like I know the next number, 7, 8, and I keep going. I can count, I just count to infinity. Then there's what's called uncountable infinity or infinitely uncountable. This is a larger type of infinity where you can't list all the elements. For example, you can't list all the real numbers, even between 0 and 1, because there are infinitely many of them. So they cannot be counted one by one. So for example, if I say 0.1, okay, what's the next real number after 0.1? Is it 0.11? Is it 0.0001? Is it 0.100001? Like that's what I mean. You just like whatever number you can say, I could say a number that's closer. Okay. So that's what I mean. So if something is infinitely countable, like the natural numbers, it's a quote unquote smaller amount of infinity than something that is infinitely uncountable, like the real numbers. Okay. And so the argument that is presented in the text, and I will try to show with you here, is what's called Cantor's diagonal argument. And so one of Cantor's key ideas is to show the real numbers are uncountable, is this diagonal argument. I will attempt to walk you through it. It's a little confusing. And what this actually relates to is if you think all the way back to chapter 1, we played this game called Dodgeball, um, where it was like X's and O's, and you would just pick a different number. If they picked X, you would pick O, so on. Okay. And what he showed that if you tried to list all the real numbers between 0 and 1, you'd always be able to find a new number that isn't on your list. Okay, this proves there are more real numbers than natural numbers. So in short, Cantor's theory revolutionized our understanding of infinity by showing that not all infinities are equal. Some are bigger than others. All right, so I'm going to walk you through this proof, and it's shown here. So in the slides, there's going to be there's this link. You can also read through it. And this diagonal proof we should mention is what's called an indirect proof. That is, you assume the opposite of what you want to true. So we're going to start with the assumption that they are equal. And you start to reason until you come to a statement that is known false. It's like, oh, well, then if I assume they're equal, this shouldn't have happened. Then we know, or so logically it tells us, the opposite of what we tried to prove is incorrect. Okay? So what we wanted to prove in the first place is true after all, that they're different sizes of infinity. Okay. So the diagonal argument starts off by representing the real numbers as we did in school. You write down a decimal point and then put an infinite string of numbers afterwards, whatever. So you can represent integers, fractions, repeating and non-repeating, and irrational numbers all by the same notation. Just represent them all this way. Okay. Integers would just be like, if you pick the number 1, it would just be 1 and then an infinite number of zeros. Non-repeating fractions, like 1/4 would be 0.25 and then an infinite number of zeros. Repeating fractions, this is 1, 2, 3, 1, 2, 3, so on, and then irrational numbers here. So we're using an indirect proof. So we wanted to prove that you could not put the real numbers into a one-to-one correspondence with all these natural numbers, 1, 2, 3, so on. So we started with the assumption you could. So to make things simple, though, we're just going to look at the real numbers between 0 and 1. If those numbers can't be put into a one-to-one correspondence with the counting numbers, then the rest of the points on the infinite line sure couldn't either. Okay. So a partial list of a one-to-one correspondence might look something like this. Again, this isn't to be taken too literally, but it's just like, the number 10 might represent 0 and then an infinite number of zeros. 1, 2, 8, 3, whatever. Could represent 0.5 and an infinite number of zeros. And all these different numbers, remember, we're saying there's an infinite number between 0 and 1 of real numbers, and there's an infinite number of natural numbers. And for whatever reason, this is the correspondence, and it would just go on forever. Okay. In the left-hand list would be the natural numbers, and in the right-hand list here would be the real numbers. All right. But partial hypothetical lists won't help us prove the theorem, so what we need is a more general representation. Okay. So this is the pattern we're going to dream up. Here's the first number, in the natural numbers 1. And it's going to correspond to number 0 point, and then these are all decimal numbers. And so what D111 says, it's digit in row 1, place 1. This one here is digit in row 1, 1, 2. Row 1, digit 2. This is the third digit, and that corresponds to 1, third digit, so on. Okay, so like D33, okay, that is the third digit that corresponds to the third number in the list. Okay, so like right here, digit 39. Okay, this is the 9th digit of this number that corresponds to the number 3. That's all this is saying. Okay. Now, if it's true there's a one-to correspondence with the counting numbers and the real numbers, then it would be impossible to find another real number that is not on your list. But what happens if we do find some real number here that does not map over here? Okay, then we found our contradiction. And if we find a contradiction, that means our initial assumption that there is a one-to-one correspondence can't be true. And that would mean that the infinity of the real numbers is not the same infinity as the counting numbers, the natural numbers, okay? That is, the two sets do not have the same cardinality. All right, it turns out that our mysterious number is very easy to write, and we'll call it M for missing. And it's just M is equal to 0 point, and then this is the trick. The first digit, all right, is diagonal 1, 1 plus 1. Second digit is diagonal 2, 2 plus 1. Huh? Digit 3, whatever the third number is here in this digit, we just add 1 to it. So if it's 4 here, it becomes 5 in this number. Okay? And so on. In other words, you take the diagonal elements of the original list. Okay, you keep going on forever, and then just add 1 to them. Okay? So this is some real number. And if our assumption that the real numbers and these counting numbers, natural numbers, have a 1-to-1 correspondence, okay, is true, then m must be somewhere in the original list. Well, here's the thing. This number m, it can't be in the first list, okay? Because my number is defined as whatever this number was plus 1. And then you know what? It can't be in the second list, okay, because it's different from this number. It can't be in the third list because it's different from this number. It can't be in the fourth list because it's different from this number. It can't be in the fifth list because it's different from this number. It can't be in the sixth list because it's different than the sixth digit in that list. All right. And if our assumption, so here, whatever number you pick, okay, all right, there is no place in the whole list where you can put the number because I can always find a diagonal. Like if you were like, let me take the 15th digit. Well, I would just go to my original correspondence in row 15, find digit 15 and add 1 to it. Okay. So though for any counting number n, the new number cannot be put in list since the original list had the nn in it. And our original will always have whatever diagonal plus 1. All right. So what that means is the counting numbers cannot be put into the counting numbers, natural numbers cannot be put into a 1-to-1 correspondence with real numbers. Okay. So they do not have the same cardinality. So there are some infinities that are bigger than others. And so this was just like, I know it's so weird, but it's just the dodgeball example from chapter 1. Okay. It's just showing that whatever you pick, I can find something different. Okay. We can do this forever to infinity. Whatever number you pick, I can find one that's different that's not on your list. So let's do a mindscape here. Okay. So this was taken from the textbook. And it says, consider the infinite collections of circles below. So you have circles that go on for infinity. And suppose you have 2 markers, one red and one blue. And you color each circle one of the 2 colors. So I could go red, 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 blue, red, 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 whatever. I do it. It doesn't matter. So how many different ways can you color the circles? All right. Obviously, you could do it in an infinite number of ways. Okay. So do you think that the set of all possible circle colorings, all right, have the same cardinality as the set of all natural numbers? Right. Like I'm just coloring, red, blue, red, blue, red, blue. That's it. Does it have the same cardinality as 1, 2, 3, 4, 5, 6 forever? Well, suppose that the set of all possible colorings was the same as the natural numbers. Then there would necessarily exist a 1-to-1 correspondence between the colorings. That is, we could list all the possible colorings. Now, suppose you have that list in front of you. If you use that diagonalization argument, I can always create a new coloring that isn't on the list. All right. So if the first circle is red, all right, paint the first circle in the new coloring blue, and so on. Like I can always pick something that you cannot map to. And you can continue in this way, changing the color of the nth circle and the nth coloring. This procedure defines a new coloring and by construction is different from all the colorings on the alleged list. So no, there's not. They're not the same cardinality right here by that diagonal argument. All right. I know this was a little confusing. And I encourage you to read the textbook. And as always, reach out to me if you have any questions.